Hello students, you're welcome to edumathub. In this video, we're going to be taking some very important questions for Jamb 2025 physics. The topic is elasticity, okay, or Hooke's law. So let's take the first question. So we are told that a force of 1.8 Newton extends a wire by 0.4 cm. Then we are told that what force will extend the wire by 1.25 cm if the elastic limit is not exceeded. So let's get the values out first. So the first value of the force is 1.8 Newton. So the extension, the first one is 0.4 cm. The second extension is 1.25 cm. So don't forget that for Hooke's law, the force applied, F, is directly proportional to the extension, provided that the elastic limit is not exceeded. So you have F equals to KE, where F is the applied force, K is the force constant, and E is the extension. So you need to first of all find the force constant first, because this is a constant, it doesn't change for this particular wire. We're talking about the same wire in this case. So the force here, F, and the extension E, will be used to get the value of K. So once I've gotten the value of K, I use it to find the value for the second force for this extension. So let's start with the first one. So we have F equals KE, so you have 1.8 is equals to K. E is 0.4 cm, but you must convert it to meters first before you use it. So you have to divide this by 100. Divide this value by 100. So you're going to get 0.004. So from here you can find K. So K is 1.8 divided by 0.004. So this K, you can just leave it like this. Instead of evaluating it, you can leave it like this. So now we're going to find the force now, the new force. But now the extension has changed. The extension is now 1.25 cm. So convert this to meter first. So you divide this by 100. So you're going to have 0.0125 meters. This is the new extension now. So what will be the force? The formula still applies. F equals to KE. So our K is already here. This is our K here. So we're looking for the force now. So the K, our K is 1.80 divided by 0.004. We will multiply it by the new extension, which is 0.0125. So if you divide this, you're going to get 5.6 Newton. Okay, well, that's the answer. 5.6 Newton. So for the next question, we are told that if a force of 15 Newton stretches a wire from 20 meters to 20.01 meter, what is the amount of force required to stretch the same material from 20 meters to 20.05 meters? So we need to first of all find the extension first. So F equals to KE from Hooke's law, as you know. So the first force that they gave to us is 50. So that means F is 50. So then you have K. Now for this first one, you need to find the extension first. This is the original length. This is the new length. The formula of extension is equals to new length, or L2, minus original length L1. So you need to subtract 20 meters from 20.01 meters to get the extension. So you will do 20.01 minus 20. So this answer will give you 0.01. Okay. Now this is the extension here. So you need to use this value to find the value of the force constant, which is K. So you just put the value of the extension, which is 0.01. So from here you can find K. So K will be 50 divided by 0.01. So let's quickly do this. Let's multiply the bottom. That will give you 50 times 100 divided by 1. You can press it to calculator straight up, but I just want to work it out. So this is the same thing as 5,000. So that's the value of K. So K is 5,000. Don't forget that the force constant is unique. It's constant for a particular material. So in the second case, or second instance, they are told to find the force. Which force will cause this extension? Okay, don't forget that the value of k is 5,000. But which force will cause this extension? So you need to find the new extension now. So the new extension is L2 minus L1. But what is L2? L2 is 20.05. So 20.05 minus the original length 20. That will give us 0.05. So that is the new extension now. But F is equals to KE. Don't forget, and our K is 5,000. So just put F is equals to KE. So K is 5,000. This is the extension here. So F is 5,000 times the extension 0.05. This is the same thing as writing 5 times 10 to the power 3 times 5 times 10 to the power minus 2. When you express 0.05 in standard form, it will give you 5 times 10 to the power minus 2. Then from here, you times these two together, that will give you 25. So you have 25 times, then 3 minus 2, that will give you 1 times 10 to the power 1. This is the same thing as writing 25 times 10. So the answer will be 250 newtons. The answer is 250 newtons. You can see that's option C. So let's take the next question. We are told that the extension in a string, when 5 gram weight was hung from it, was 0.56 centimeter. If Hooke's law is obeyed, what is the extension caused by 20 gram weight? So let's get the forces first. So WT there stands for weight. So the first one is a 5 gram weight. That is 5 gram weight. That's the first one. Okay, the second one is 20 gram weight. So you can see that the answers are in centimeters. Okay, so you can just leave the given extension in centimeter, 0.56. Don't need to convert it. So you know that F is equals to KE, right? So from here, you can easily get your K for the first one. So K will be F divided by E. And our F is 5 gram weight, or 5 divided by 0.56. So you can leave this like this instead of converting it. So this K is the first constant. We're going to use it to find the extension for 20 gram weight, which is what we are supposed to look for in the question. So we know that F is equals to KE, and our E will be F divided by K. So our F is already given in the question, that's 20. So that will be 20 divided by, the value of K is already here, everything like this. So just put it underneath it like this, 5 over 0.56. So you just apply simple fractional division. So that will be 20 times 0.56 divided by 5. 5 here 1, 5 here will give you 4. So you have 56 times 4, 0.56 times 4. So 56 times 4 will give you 224. 224. Then you see the decimal point has 2 places, so the point will be here. So the answer is 2.24 centimeters. It is not there at all. It is not among any of the options. But the answer itself is 2.24. That's the required answer. Just that it is not in the option. Okay, so let's take the next one. So for number 4, a 10 gram mass placed on a pan of a spring balance causes an extension of 5 cm. If a 15 gram mass is placed on the pan of the same spring balance, the extension is what? So you know that your F is KE. So the first gram mass is 10, that is the first weight. The extension for the 10 gram is 5 centimeter. So you put 5 here. So your K will be 10 over 5. So your K is 2. So after getting the value of K, all you need to do is to use to find the extension for the second mass. The second mass is 15 gram mass. So looking for the extension. I know that this K is always constant. That's the first constant. And your normal F will still be KE. So our F now is 15 gram. Okay, so just put 15 here. Our K is 2. Our E is still normal like that. So our E will just be 15 over 2. So 15 over 2 give you 7.5 cm. So the answer to this question is 7.5 cm. For number 5, we're told that the spring extends from a length of 10 cm to 10.01 cm. When a force of 20 Newton is applied to it, to find the force constant. You know your force constant is K, and your F from Hooke's law, F is KE. So you can find k. K is F over E. So we're looking for k, which is the first constant. So let's check. So the length changed from 10 cm to 10.01 cm. So the extension there, you can easily find it. That is 10 L2 minus L1. Okay, L2 in this question is 10.01. Okay, so 10.01 minus 10, 10.01 minus 10, that will give you 0.01. So this is the extension, but this extension is in centimeter. You need to convert it to meters. So you divide this by 100. So that will just give you 4 zeros, 0.0001 meters now. This is the extension. So that's what you're going to slot into the formula for F equals to KE. Just come here, K will now be F divided by 0.0001. But don't forget, on the question, F is 20 newtons. So K will be 20 divided by 0.0001. So you divide this, K will be, let me just times by 1, 2, 3, 4. So just times this by, the answer will be 200,000. Once you in standard form, you write it as 2 times 1, 2, 3, 4, 1, 2, 3, 4, 5. There are 5 zeros. 2 times 10 to the power 5. So let's check it out. Times 10 to the power 5 Newton per meter squared. So we'll move to number 6. The total length of a spring when a mass of 20 grams is hung from its end is 14 cm. That's total length. While the total length is 16 cm when a mass of 30 grams is hung from the same end. You have to find the unstretched length. That means you have to find the original length of the spring, assuming Hooke's law is obeyed. So we're told that the first mass is 20 grams. Okay, that's the first mass from the question. Then the length, the whole length, the original length plus the extension, everything is 14 cm. That was the first case here. So original length plus extension will give you 14 cm. Then in the second case, we have the original length. The original length is always constant. So that's why it's L1, L1. It's always constant. Okay, the original length of the spring is constant. But the second extension is E2. Okay, when a mass of 30 grams is hung from the end. So the length now is now 16. So you have two equations here, equation 1 and equation 2. So you just solve this equation easily. So if you subtract equation 1 from equation 2, you will just do E2 minus E1. So these two we cancel out because they are the same value. Then E2 minus E1 will be equals to 16 minus 4. 16 minus 4 will give you 2. So you have this, call this one equation 3. Then remember from your Hooke's law that F is equals to KE. Okay, F is equals to KE. Something that is constant here is the first constant, which is K. So K is constant in this case. So you need to use the masses, as the masses that were hung, to get the extension. From there, you cannot get the first constant. The first constant is a constant. Okay, so you don't need to stress yourself because it's going to be the same for the two cases. So for the first case, we are told that M is 20 grams. Okay, M is 20 grams in the first case, as you can see it from here. M is 20 grams. The extension will be E1. So we are going to have 20 is equals to KE1. For the second case, the force is 30. So we're going to have 30 is equals to KE2. So from here, you can call this, you can just divide the equation. Let's say this is equation maybe 4 and this is equation 5. If you divide this equation, maybe E2, equation 5 divided by equation 4. So you're going to get 30 over 20 equals to KE2 over KE1. So from this part, you get 3 over 2, K cancel K. So you're going to get 3 over 2 is equals to E1, E2 over E1. Okay, so this relationship between E2 and E1. 3 over 2 equals E2 over E1. But don't forget that you only have a relationship for E2 and E1, which is E2 minus E1 is equals to 2. Okay, and you have on that one here, 3 over 2 equals E2 over E1. So you just need to solve these two equations simultaneously. So from this part here, let's substitute for E2. So E2 will be equals to, take E1 to this side. So you're going to get 2 plus E1. Now, this equation, substitute inside this one here. So you're going to get 3 over 2 is equals to, now you have E2 here. Instead of writing E2 in this part, you're going to write 2 plus E1. So I'll just write 2 plus E1 over, this is E1 at the bottom part, this will give me E1. So I'll cross multiply now, like this. So this will give me 3E1 is equals to 2 into E1 plus 2. So I'll just expand this. 3E1 is equals to 2E1 plus 4. Collect the like terms. 3E1 minus 2E1 is equals to 4. From here, E1 will give you 4 centimeter. That means the extension is 4 cm. E1. But we're told to find the original length, which is L1. So, but we know that E1 is 4. So just come and put it inside here. So this E1 here is 4. Okay, from the calculation that we just did. So this equation 1 will become something like this. L1 plus E1 equals to 14. It will not look like this. L1 plus E1 is equals to 14. Now be L1 plus 4 is equals to 14. So L1 will be 14 minus 4. L1 will now be 10 cm. So the value of the original length is 10 cm. So go and look for 10 cm in the question. So that's number 6. So 10 cm. You can see it from here. Option B. So that's the answer to that question. So let's move to the next one. So for number 7, we are told that a force of 100 Newton stretches an elastic string to a total length of 20 cm. If an additional force of 100 Newton stretches the string 5 cm further, or to find the natural length of the string. So it's very straightforward. Anytime you see natural length, all you're looking for is L1. Okay, anytime you see natural length, all you're looking for is L1. So L1, which is the original length, plus the extension, everything should give you 20. Okay, we were told that an additional force of 100 Newton, like they applied an additional force, and that force caused the string to stretch 5 cm further. So you can pick it from there that the extension for 100 Newton, is 5 cm. Because when the force of 100 Newton was applied, the string stretched by 5 cm. So that means 100 Newton will cause an extension of 5 cm. So it's very easy to understand. So that means the original force that was applied at first, the 100 cm force, will cause an extension of 5 cm. That means E is equals to 5. So just come to this equation here and put E is equals to 5. So all you're going to get is L1 plus 5 is equals to 20. Then from here you can get L1 equals to 20 minus 5, which will further give you L1 is equals to 15 cm. So the original length or the natural length of this string is 15 cm. So for number 7, 15 cm. So the answer is option A. It was told that the spiral spring of a spring balance is 25 cm long when 5 Newton hangs on it. Okay, and it is 30 cm long when the weight is 10 Newton. So to find what is the length of the string or the spring if the weight is 3 Newtons, assuming Hooke's law is obeyed. So you need to break this question down in like several stages. So the spiral spring is 25 cm long when 5 Newton hangs on it. That is the original length L1 plus the extension. Everything will give you 25. Okay, that's for the first case. Okay, then for the second case, that is for the force of 5 Newton. So this first extension will be E1. That's what you're going to call it. So yes, for the second case, everything stretched by 30 cm. So your L1, which is constant, plus the second extension, which is E2, will give you 30. But this one is caused by the force of 10 Newton, as you can see from here. The force of 10 Newton, that's what's causing this extension. So this one will be 10 for the force of 10 Newton. So from here, you can see that you can easily find the relationship between E1 and E2 when you subtract. So let's subtract this equation from this equation. So if you do that, you can see that L1 will cancel out because they are the same value. Then you're going to have E2 minus E1. E2 minus E1 is equals to then 30 minus 25. That will give you 5. Okay, so that's the relationship between E2 and E1. Now, looking for something. The next thing to find is to find the force constant, which is K. You need to find the spring constant, which is K. Now, how will you do that? Look at the first force, which is 5 Newton. 5 Newton, you know that your F is equals to KE. So for the first force, which is F1, that is F1 is equals to KE1. So F1 is 5. this will give you K. The extension caused by the 5 Newton force is E1. Then try for the second force, which is F2. So this one will give you 10 Newton, or 10 is equals to K E2. So you have this equation and this equation. So from here you can find another relationship between E1 and E2. K is a constant, so it can easily disappear when you divide. So let's divide this equation by this equation. So you're going to get K E2 divided by K E1 is equals to 10 over 5. K cancel K. So you can get E2 over E1 is equals to 10 over 5 is 2. So from here you can find the relationship between E2 and E1. So you can say E2 cross multiply, that will give you 2E1. So E2 is equal to 2E1. Come to this place back. E2 is equal to 2E1. E2 is 2E1. So anywhere you see E2, just write 2E1 there. So come and substitute it into this equation here, into this one. So you have, instead of writing E2 here, just write 2E1, because E2 is equal to 2E1. So you have 2E1 minus E1 is equals to 5. And here E1 is equals to 5. So that means the first extension is equals to 5 cm. So if the first extension is 5 cm, you can easily get the original length by substituting it into the original equation, which is this equation here. Substitute into this part. So E1 is 5. Okay, E1 is 5. So if E1 is 5, then what will be L1? What will be L1? So let's put 5 here. Okay, so if you put 5 there, so you're going to get L1 plus 5 is equals to 25. So L1 is equals to 25 minus 5. Then you're going to get L1 is equals to 20. That means the original length of this string is 20 centimeter. Okay, now you can see that everything is almost obtained. What you are told to find in this question, you have to find the length of this string if the weight 3 Newton is applied. So you need to find the natural length plus the extension caused by 3 Newton. But before you can find the extension caused by 3 Newton, you need to know what is K for this spring. So don't forget that E1 is 5. And the force causing the extension of 5 is 5 Newton. So you can easily find K from there. You know your F is Ke, right? F is Ke. And E1 is 5. This is 5. This is K. The force is 5. So from there you can find K. So K will give you 5 over 5, which is 1. So for the force of 3 Newton, which you are told to find, you're going to have F equals to Ke again. So let's find the extension caused by that force. So F is 3 Newton now. K is already 1. We have already found it. So that will be 1 times the extension. So you can see that this force will cause an extension of 3 equals to E times 1 will give you E. So the extension caused by the 3 Newton force is 3 centimeter. But what is the original length of the material? We're going to find the whole length. So you have to do L1 plus this extension. Okay, 3 centimeter. So you need to add 3 to the value of L1. What is L1? We've done L1 here. You can see L1 is 20. So just add the extension caused by the 3 Newton force, which is 3. So you have 20 plus 3. So 20 plus 3 will give you, which is 23. So let's check the options. You can see the answer here, 23 Newton, which is the correct answer to the question. Okay, so we'll move to number 9. A force of 15 Newton stretches a spring to a total length of 30 cm. An additional force of 10 Newton stretches the spring 5 cm further. You have to find the natural length of the spring. A question like this, you can see an additional force of 10 Newton. Just look at the length that it caused, or the extension that it caused. So additional length of 10 Newton stretches the spring 5 cm further. That means the extension for 10 Newton is 5 cm. So when the force is 10 Newton, the extension is 5 cm. Okay, you can easily find K now. F is equals to Ke. So this is 10, the force is 10, K is the constant, then we have 5. From here you can find K. So you see that your value for K will be k equals 10 over 5. So k is 2. So if k is 2, you can easily find the extension caused by only the force of 15 Newton. Don't forget k is 2. So that will be F equals to KE a second time. But now the force is 15 and K now is 2. But what will be the extension for that force? So E now will be 15 divided by 2. So you can see that the extension caused by only this force will be 7.5. But we are told on the question that the whole length of this the string was 30 cm. That means L1 plus the extension was 30. Okay, L1 plus the extension was 30. You have to find the natural length. Natural length means you have to find L1. That's means of natural length. So that means L1 will be 30 minus the extension for 15 Newton. And what is the extension for 15 Newton? That is 7.5. So just come here and do 30 minus 7.5. So that will give you 22.5, which is the natural length of the string. So go to your option and look for 22.5. So you can see it as option B. So the answer to number 9 is option B. So for number 10, we are told that a piece of rubber 10 cm long stretches 6 mm when a load of 100 Newton is hung from it. What is the strain? What is the strain? So you need to know the meaning of strain first. Okay, strain has to do with the extension divided by the original length. So the formula for strain is extension divided by the original length. So look for the extension first, then divide it by the original length. Okay, that's the formula for strain. Pick out the values from the question. So you can see that the natural length is 10 cm. Okay, natural length is 10 cm. So L1 is 10 cm. Then the load of 100 Newton causes it to stretch by 6 mm. So the extension, which is E, the extension is E, that is 6 mm. But they are not in the same unit. You need to convert them to the same unit. So let's convert them to centimeter. So to convert millimeter to centimeter, you divide it by 10. So this extension, if you convert it to centimeter, that will be 6 over 10, which is 0.6 centimeter. So now we have the extension and we have the original length. Extension that we got was 0.6. So we are dividing by the original length, which is 10. Okay, so this is in centimeter, this one too is in centimeter. So if you divide these, you're going to get 6 times 10 to the power minus 2, or you're going to get 0.06. Okay, any of them is correct. Don't forget, strain does not have any units because it is dimensional. Centimeter cancels centimeter. So the answer is 0.06 or 6 times 10 to the power minus 2. So that's option B. Sorry, that's option C. Okay, option C is the correct answer. 6 times 10 to the power minus 2. So let's take the next question. So for number 11, we are told that a load of 20 Newton on a wire of cross-sectional area 8 times 10 to the power minus 7 meters squared produces an extension of 10 to the power minus 4 meters. We have to calculate the Young modulus of the material of the wire if its length is 3 meters. So this is Young modulus. Okay, but first of all, if we talk about Young modulus, let's pick out the values from the question. So a load of 20 Newton, okay, that's the force. So F is 20 Newton, as you can see from the question. Then the area here is 8 times 10 to the power minus 7. So area is 8 times 10 to the power minus 7 meters squared. The extension is 10 to the power minus 4 meter, 10 to the power minus 4 meters. Then we are told that the original length is 3 meters. So L is 3 meters, or L1. But the Young modulus has a formula. Young modulus is equals to stress over strain. But you can also write it as FL over AE. This is the formula for Young modulus. FL over AE. And you already have all the values that you need here. So what is our F? That is 20 times. What is our L? That is 3. Divided by, what is our area? That is 8 times 10 to the power minus 7. 8 times Then what is our extension? That's 10 to the power minus 4. So let's multiply the top first. So 20 times 3, that will give you 60. The bottom part is 8. So apply indices here. You add these two powers together because times means plus in indices. So that will give you 7 plus 4, that will be 10 to the power minus 11. So apply a simple trick here. Take this 10 to the power minus 11, take it upwards, take it to the numerator. So when it gets there, the sign will change to plus. So instead of minus 11, you're going to get plus 11. Okay, so this will become 60 times 10 to the power 11. So no more minus anymore. Okay, divided by, then you have 8 at the bottom part. So all you have to do is divide these two together. 60 divided by 8, that will give you 7.5. Okay, so you have 7.5 times 10 to the power 11. So that's the Young modulus. So let's check it out in the option. So 7.5 times 10 to the power 11. So you can see it from here. Option B. So for number 12, we are told that the tendon in a man's leg is 0.01 meters long. If a force of 5 Newton stretches the tendon by 2.0 times 10 to the power minus 5 meters, but to calculate the strain on the muscle. You know, strain normally is extension over original length. Look for the extension first, divided by the original length. That is strain. So check the question first. Let's look for the strain. So the tendon in the man's leg is 0.01 meters. So that means the original length is 0.01 meters. So you have 0.01 on the bottom part. So let's find the extension. From the question, you see that the extension is 2.0 times 10 to the power minus 5. So that will be at the top. 2 times 10 to the power minus 5. So all you have to do is simplify this. So if you simplify this one, the bottom part is the same thing as 2 times 10 to the power minus 5 divided by 1 times 10 to the power minus 2. Okay, 0.01 is 1 times 10 to the power minus 2. Just take this one to the top there. By the time it gets there, it's going to be plus. So you have 2 over 1 times 10 to the power minus 5 times 10 to the power 2. So do indices here. Apply indices here. So that will give you minus 5 plus 2. That's minus 3. So you're going to get 2 times 10 to the power minus 3. That's the answer. Or 0.002. So let's check it in the option. So for number 12, 2, that is option C. So you can see it here. 2 times 10 to the power minus 3. Option C is the answer. Okay, let's take the next one. So let's continue. If the stress on a wire is 10 to the power 7 Newton per meter squared, and the wire is stretched from its original length of 10 cm to 10.05 cm, but to find the Young modulus of the wire. So let's pick the data from the question. The stress is 10 to the power 7, as you can see here. That's the stress, 10 to the power 7. The original length is L1, which is 10. So this is 10 here, that's the original length. Then the new length is 10.05. Okay, 10.05. That's the new length, also in the question. So you need to find the extension first. So let's find the extension now. So the extension will be E equals to L2 minus L1. Okay, L2 is 10.05 minus 10. So this will give you 0.05 cm. Okay, 0.05 cm is the extension. So let's talk about Young modulus now. Now, you need to understand the Young modulus. Young modulus can be defined as stress over strain. That's the Young modulus, stress over strain. So in this question, they've given you stress already. They're giving you the stress, which is 10 to the power 7. Okay, so this equation will just look like this. So you're going to have 10 to the power 7 divided by the strain. What is the strain? The strain is always extension over original length. That's the formula for strain. So strain is extension divided by the original length. The extension in this question, which we just found, is 0.05. So that will be 0.05. You divide that by the original length. The original length in this question is L1. What's L1? L1 is 10. Okay, so you're going to put 10 under this part here, 10. So if you divide this by 10, you're going to get 0.005. So this is the strain. Just carry this value and come and plug it into the value for the Young modulus. So if you plug that in, you're going to get you're going to get 10 to the power 7 divided by 0.005. So 0.005 can be written in standard form as 5 times 10 to the power minus 3. So you're just going to get 10 to the power 7 divided by 5 times 10 to the power minus 3. Okay, and this 10 to the power 7 is the same thing as 1 times 10 to the power 7 divided by 5 times 10 to the power minus 3. So 1 over 5 here is 0.2, right? So 0.2 times, you take this 10 to the power minus 3, take it to the top here, take it to the numerator, it's going to become plus when it gets there. Okay, so you have 10 to the power 7 times 10 to the power 3. So apply indices. This is the same base, just add the powers. Just give it times 10 to the power 7 plus 3 is 10. And you have 0.2 on this side. Now 0.2 in standard form is 2 times 10 to the power minus 1 times, then you have 10 to the power 10. So another indices again. So just add the powers since the middle is times. Times means plus in indices. So you're going to get 2 times 10 minus 1 or minus 1 plus 10 will give you 9. So you have 2 times 10 to the power 9. So that is the answer. So you can see it here, that's option D, 2 times 10 to the power 9. Okay, so let's take the next question. So for number 14, we are told that a spiral spring of natural length 30 cm and a force constant of 20 Newton per meter is compressed to 20.0 cm. To calculate the energy stored in the spring, So you can see that the natural length, which is L1, is 30 cm. The force constant, which is K, is 20 Newton per meter, and the new length after the compression is 20.0 cm. So look at the values here. I've already brought them out for you. So L1 is 30, L2 is 20, then K is 20 Newton per meter. So you need to know that the energy stored in a spring can be obtained from this formula. W is equals to half KE squared. This formula is very important. This is the formula for the energy stored in a string. You can also replace this W by E, capital E. So that's half KE squared. So this E is the extension, K is the force constant. Okay, so let's find the extension in this question. Extension is always E equals to L2 minus L1. So just subtract. So 20 minus 10, that will give you 10. You don't need the negative sign. So, or 30 minus 20, that will give you 10. So the extension is 10 centimeter. But we need to convert it to meters. So if you convert 10 cm to meters, just divide it by 100. So 10 over 100, that will give you 0.1 meters. So the extension is 0.1. So plug everything into this equation. Okay, and don't forget that the value of K is 20. So you're going to get 1 over 2 times 20 times 0.1 squared. So 2 here 1, 2 in 20 is 10. So you're going to get 10 times 0.1 squared, which is the same thing as 10 times 0.1 times 0.1. 10 times 0.1 will give you 1. Then 1 times 0.1 will give you the final answer as 0.1. So the answer is 0.1 joules. Because this is about energy. So check the option. 0.1 joules. That's the correct answer. 0.1 joules. So let's take number 15. So for number 15, we're told that an elastic string of force constant 200 Newton per meter is stretched through 0.8 meters within its elastic limit. To calculate the energy stored in the string. So the force constant is K, which is 200, and the extension is 0.8 meters. So E is 0.8. But what is the formula for the energy stored in a string? That is capital E, or W, is equals to half KE squared. So you already know what's K, right? So that will be half times 200 times 0.8 squared. 2 here 1, 2 in 200, that's 100. So I'm going to get 100 times 0.8 squared. That's 100 times 0.8 times 0.8. If you multiply that out, you're going to get 64 joules. So the answer is 64 joules, as you can see. 64 joules. 64 joules. Now let's go for number 16. For number 16, a spring of force constant 1500 Newton per meter is acted upon by a constant force of 75 Newton. To calculate the potential energy stored in this string. The potential energy stored. The formula of potential energy stored is equals to, there are two formulas for it. You can use W equals to half Fe if they give you the force and just the extension. But if they give you the value of K, it's going to be half Ke squared. So these two formulas will give you the same answer. But from this question, you can see that the force constant is 15, while the force is 75 Newton. But they did not give us the extension. So the force constant is 15, while the force is 75 Newton. So you need to find the extension, or just substitute anyone you like. So let's use the formula W is equals to half Fe. Okay, half Fe. Don't forget that originally F is equals to Ke. Okay, F is equals to Ke. And from here, you can make E the solution formula. E will be equals to F over K. So just come here, instead of writing E, just write F over K. So that will be half times F over K. And your F is 75, while your K is 1005. So just substitute and you get your answer. So you have half times 75 times 75. And you divide this by 1500. So this top here, which is 75 times 75, that will give you 5625 divided by then 2 times 1500, that will give you 3000. So if you divide 5625 by 3000, you're going to get 1.875, which is the same thing as 1.88 or 1.9 joules. The answer is 1.9 joules. That's option A. So option A is the answer, 1.9 joules. For number 17, we are told that when a force of 50 Newton is applied to the free end of an elastic cord, an extension of 4 cm is produced in the cord. We have to find the work done. We know that your work done is half Fe. Okay, that's the formula for work done. There's another formula, half Ke squared. That's if you are given the force constant. But I don't think we are going to be using this formula here. So let's find the extension. The extension in the question is 4 cm. Let's convert it to meters. So we divide 4 cm by 100. That will give you 0.04. And our force already is 50. So that will give you half times 50. The extension now is 0.04. So 2 here 1. 2 into 50 is 25. So you have 25. So you have 25 times 0.04. So if you multiply that, you are going to get 1 as the answer. 1 joule. Or just 1. So let's check that. So we check the answer for number 17. The answer is 1 joule. Okay, 1.0 joule. So let's go to the next set of questions. For number 18, we are told that a spring of length 25 cm is extended to 30 cm by a load of 150 Newton attached to one of its ends. What is the energy stored in the spring? So it's very easy. Let's find the extension first. So we have 25 as the original length and 30 as the new length. So subtract that, 30 minus 25, so that will give you the extension as 5. So 5 cm is the extension. So convert it to meters first, so divide it by 100. So that will give you 0.05 meters. So once you've gotten the extension, the force is already there, which is 150. So the force is 150, right? So force is 150. So put it in the formula for energy stored in a spring, which is half Fe. So you're going to get half times 150 times 0.05. Okay, so 2 here 1, 2 in 150 is 75. So this will give you 75 times 0.05. If you multiply that, you're going to get 0.75 joules. Okay, so let's check it in the option. So 3.75 joules, that's option C. Okay, option C is the answer. For number 19, we are told that the energy stored in a wire when it is extended by 0.02 meters by a force of 500 Newton is. So the extension is 0.02 and the force is 500 Newton. Just plug it into half Fe. Okay, so you have half times the force is 500. The extension is 0.02 times 0.02. So you're going to get 2 here 1, 2 in 500, that's 250. So you're going to get 250 times 0.02. So 250 times this value will give you 250 times 2 is 500. Okay, so you just put the decimal places, which is point as 22. So you're going to get 5 joules as the answer. 5 joules. So 250 times 0.02 will give you 5 joules or 5. So let's check it in the option. 5 joules, that is option A. So option A is the answer, 5. So let's go to number 20. So for number 20, we are told that a spring is compressed by 0.03 meters. That's the compression, okay, which is the extension. To calculate the energy stored in the spring if the force constant is 300 Newton meters. Okay, so K is 300, E is 0.03. So plug it into the formula. W is equals to half Ke squared. So that will be half times W is 300, extension is 0.03 squared. So if you solve this, you're going to get 1 over 2 times 300 times 0.03 times 0.03. Okay, that's the meaning of 0.03 squared. So this will give you 2 here 1, 2 in 300 is 150. So you have 150 times. So this part here can be written as 3 times 10 to the power minus 2 times 0.03 is also 3 times 10 to the power minus 2. Use indices and add these two guys. That will give you 10 to the power minus 4. 2 plus 2 is 4. Then 150 times 3 times 3. That will give you 1350. So then if you multiply these two, you're going to get 0.135 as the answer. 0.135 joules. So go to the option and look for the answer there. So 0.135 joules, that is the answer to that question. For number 21, we have to calculate the work done to stretch an elastic string by 50 cm if a force of 12 Newton produces an extension of 5 cm in it. So this is the extension here, as you can see, 5 cm. Okay, then this is the force that you are given. So to solve this question, you need to bring out the values first. So the work done to stretch an elastic spring by 50 cm, that's what you are looking for. So let's say E2 is 50 cm. But the force of 12.5 Newton, which is F, cause an extension of 5 cm. Okay, that's E1. So E1 is 5 cm. So before you can find the work done by this extension, you need to find the value of K first. So let's do K. So to find K, you're going to use F equals to Ke. F equals to Ke. So F is 12.5 equals to K times, and this is 5 cm. You have to convert it to meters first. So you divide it by 100, okay? So that will be 0.05. So my K will be 12.5 divided by 0.05. If you divide this, you're going to get 250. So the value of K is 250. And don't forget, K is a constant. So use this value of K to find the energy or the work done produced from this extension of 50 cm. So to do that is very easy. All you have to do is just use the formula. Work done is half ke squared. But our extension is 50 cm. We need to convert this to meters first. So that will be equals to 50 divided by 100. That will give you 0.5 meters. Okay, so come and plug it into this formula here. So you will get, your k is 250, don't forget. So you're going to get half times 250 times 0.5 times 0.5 squared. So if you solve this, you're going to get 2 here 1. 2 in 250 is 125. So you have 125 times 0.5 times 0.5. If you multiply everything, you're going to get 31.25 joules, which is the answer. So check it in the option. So that's it there. That's 1.25 joules. That's the answer to the question. So let's take the next one. A spring of force constant 500 Newton per meter is compressed such that its length shortens by 5 cm. Okay, we have to find the energy stored in the spring. So you can see that 500 Newton per meter is K, 5 cm is the extension. Plug it into the formula half Ke squared. So K is 500, extension is 5 cm. So half Ke squared, half times 500. Now extension is 5 cm, but you cannot use it here. You have to convert it to meters. So divide it by 100. That will give you 0.05. So times 0.05 squared. From this point, you're going to have half times 500 times 0.05. Then from here, 2 here 1, 2 in 500 is 250. So you have 250 times then just multiply all this to get your answer. If you multiply this, you're going to get 0.625 joules. 0.625 joules. That's option A. For this next question, I have to use the data in the table below to determine the length x of a wire, assuming Hooke's law is obeyed. So you can see the force applied was 0 at first. Then the length was 800 millimeters. So this is the original length without any force being applied. That is the original length. But when they applied the force of 5 Newton, the whole length, new length plus extension, everything changed to 801. So from 800, it became 801. From there, you can easily find the extension. So extension is L2 minus L1. So this is L2, this is L1. If you subtract that, 801 minus 800, you're going to get 1. So that means the extension is 1 in this case. But what will be the force constant of this string, which is constant? It will be the same for all the old values used. So the force constant will be F is equals to Ke. What is F? F is 5. Okay, so 5 is equals to K times 1. So that means K is equals to 5. So that means the force constant is 5, which applies here, which also applies here. If the force constant is 5, you can find the extension caused by this force of 50 newtons. So just put it into the formula. So the force is 50 newtons now, so F is equals to 50. I know that your K is 5. So let's find the extension. F is equals to Ke. So E equals to F over K. What is F? F is 50. K is 5. Divide that, you're going to get 10. So extension is 10 millimeters. But the whole length will be the original length plus the extension. You know, the whole length will be increased. The original length, the way it was before any force, plus the extension of 10 millimeters. What is the whole length without any force being applied? Just go to your table, you're going to see there. This is the original length without any force of 0 being applied. So this is 800. So you have 800, you just add 10 to it, which is the new extension. So 800 plus 10 give 810. 810 millimeters. So the answer is 810 millimeters. Okay, that's what this force will produce. So let's take the next set of questions. We are told that a wire of length 5 meters, okay, and diameter 2.0 millimeter extends by 0.25 millimeter. When a force of 50 Newton was used to stretch it from its ends, you have to calculate the stress on the wire and the strain on the wire. So pick out the values first. The wire of length 5 meters, that means L1, which is the original length, is 5 meters. Okay, very important. Then the diameter of the wire is 2.0 millimeters. So let's convert this to meters first. So we divide this by 1000. So we divide 2 by 1000. So you're going to get 0.002 meters. Okay, so this is the diameter of the wire. Then another thing to note on the question is that the force is 50 Newton. The force is 50 newtons and the extension is 0.25 millimeters. So the extension is 0.25 millimeters. And if you convert it to meters, you're going to get 0.25 divided by 1000. So you will get 0.00025 meters. But I told that the force is 50 Newton. The first thing, you are told to find the stress. So what is stress? Stress is force over area. Okay, force over area. That's stress. So we have the force already, 50. The area is pi r squared. That's how you obtain the area, pi r squared. So to obtain the area of this material, you need to first of all know the radius. So the diameter was given to you as 0.002. So just divide this by 2 to get the radius. That will be 0.001. So the radius will be 0.001. Okay, so you're using pi r squared now. Pi r squared. 3.142 times the radius, which is 0.001. We're going to square that. 50 divided by 3.142 times 0.001 times 0.001. So from here you can easily divide this. Just divide this. So if you divide that, you're going to get 15.9. Now 0.001 can be written as 1 times 10 to the power minus 3. And this second one too, the same thing. So just take them to the top, take them to the numerator. When they get there, their signs will change to plus. So it will not be negative 3 again. It will just be ordinary 3. So you're going to get 15.9 times 10 to the power 3 times 10 to the power 3. Use indices for this part. That's 10 to the power 6. 15.9 times 10 to the power 6. But 15.9 can be expressed in standard form as 1.59 times 10 to the power 1. Then you have times 10 to the power 6 again, which is the second part. So if you finalize everything, this is indices, just add the powers. That will give you 1.59 times 10 to the power 7. Okay, Newton per meter squared. This is the stress. So you can see that there, that's the stress, which is the correct answer. Then for the second part, you have to find the strain. You already know what strain, right? Strain is the extension divided by the original length. So look for the extension divided by the original length. So for this question, the original length is 5 meters. 5 meters. And the extension is 0.25 millimeters. Extension will be 0.25 millimeters divided by 5 meter. But you can see that they're in different units. You need to put them in the same unit. So let's convert 5 meters to millimeters. So to convert from meters to millimeters, just multiply by 1000. So you have 0.25 millimeters divided by 5 times 1000 will give you 5000. That's 5000 millimeters. So they are in the same units now. So these two cancel out. So 0.25 divided by 5000. If you divide that, you're going to get 5 times 10 to the power minus 5. So don't forget that string is dimensionless, it doesn't have any units. So the answer is 5 times 10 to the power minus 5. So you can see it here, 5 times 10 to the power minus 5. Thank you for watching up to this point. I really appreciate you. Thank you, thank you, thank you. So let's take the last question. If you have not subscribed to this channel, please make sure you subscribe, okay, by clicking the subscribe button. Let's take the next question. So for number 25, you look at this question, it's very, very simple. We are told that a 50 kg block is dropped on a spring from a height of 10 meters above, as you can see in this diagram. If the force constant of the spring is 4 times 10 to the power 4 Newton per meter, you have to find the maximum compression. Maximum compression means you have to find the extension. So you just look at this diagram here. If this block is dropped from a particular height, you know the block was stationary at first, so it will have a potential energy, P. Potential energy is mgh. Okay, so when that block lands on this string, it will compress this string and make it shorter. But the energy that is going to use to compress it will be equals to this here. And that same energy will be transferred to the spring, which will give you the energy of half ke squared. So both of them will be equal, okay, because energy is always conserved from the law of conservation of energy. Energy can neither be created nor destroyed, but can be converted from one form to another. So you're going to have mgh is equals to half ke squared. Both of them will be equal. So mgh is equals to half ke squared. So you can see that they gave us acceleration due to gravity, g, as 10. Okay, we have the mass, which is 50. Then we have the height, which is 10. So k is 4 times 10 to the power 4. We are looking for the extension. So m is 50, g is 10, height is 10. Then we have half, then k is 4 times 10 to the power 4. Then we're looking for the extension squared. So if you solve this side here, if you multiply everything, you're going to get 5,000. 2 here 1, 2 in 4 is 2. Then you get 2 times 10 to the power 4 times. So to get e squared, just divide both sides by this value. So you have 5,000 divided by 2 times 10 to the power 4. 2 times 10 to the power 4 the same thing as 20,000. So you have 5,000 divided by 20,000. If you divide this, you're going to get 0.25. So that means my e squared is 0.25. So my e will be square root of 0.25. So then my e will be 0.5 meters. So the extension, the maximum compression is 0.5. So the answer is option B, 0.5. Okay, 0.5. So thank you for watching up to this point. I really appreciate you. Thank you. Please make sure you subscribe to this channel. I'm going to be posting more videos and more topics on Jamb physics. Thank you for watching. Please click the subscribe button if you have not done so. Thank you guys. Until I see you guys again in the next video. Thank you. Take care of yourself. Bye.